Hello students, welcome to JCE Connect. Subject Groundwater and Hydraulics 17 CV 742. In previous classes we have seen the definitions like porosity, then what is specific yield, specific retention, and what is the relation between these three parameters or aquifer parameters. That is N is equals to SY plus SR, that is porosity is equal to the specific yield plus specific retention. So now we will start with the one more definition, that is storativity or storage coefficient. The symbol for this is capital S. So let us discuss the definition of storativity. So it is defined as the volume of water that an aquifer releases from or takes into storage per unit surface area of an aquifer per unit change in the component of head normal to that surface. So this is the definition of storativity. So what it means? So here it is defined as the volume of water. So how much volume of water that an aquifer releases from or it takes into storage. So here we have to consider a unit surface area, okay, and what is the change per unit, okay, in the component head which is normal to that surface. That if we observe, that gives us what is the storativity of that aquifer or the storage coefficient. So it is defined as the ratio is the volume of water that an aquifer releases from or takes into storage per unit surface area of an aquifer per unit change in the component of head normal to that surface. So that is called as an storage coefficient. So the water yielding capacity of an aquifer can be expressed in terms of its storage coefficient. So here what is the meaning of that storativity is how much water a well can yield. So that is the water yielding capacity of an aquifer can be expressed in terms of its storage coefficient. So the storage coefficient can be best determined from pumping test as I had told you in the previous class also. So pumping test of the well from groundwater fluctuations in response to the atmospheric pressure or ocean tide variation. So if you have selected a well which is very near to the coast, then there will be some fluctuations because of the ocean tide variations, tides or the water waves which are coming towards the land, okay. So that is there will be a downward movement of the water also, so that will affect so with respect to that, and even with respect to the atmospheric pressure, okay, what is the yield of that aquifer is called as the storage coefficient. So storage coefficient can be determined by pumping test of the well or from the or you can observe the groundwater fluctuations which are happening in a well with respect to the atmospheric pressure or the tidal variations. So under artesian conditions, so we have discussed in previous class what is mean by artesian aquifer. So whenever there is a confined aquifer, when it is enclosed between the two impermeable layers, and if we drill a well in such aquifer, okay, wherein the pressure is more and the water will come up automatically up to the piezometric surface, that is called as the artesian well. So under such artesian conditions, when the water is released from the storage by compression of water bearing material, that is nothing but the aquifer, and by the expansion of water itself. So here if the condition is artesian, that is if it is a confined aquifer, okay, then the water is released from storage by compression of water bearing material, that is aquifer, and by the expansion of the water itself. The water also gets expanded, and that is the reason it will come out. So thus the storage coefficient is a function of what? It is the function of elasticity of water and the aquifer material. So both the elasticity of water as well as the aquifer material decides what is the storage coefficient. So these are the functions of storage coefficient, that is elasticity of water and the aquifer material. Next we'll see what is the formula for storativity or storage coefficient. So this was given by Jacob in 1950. So this formula is given by Jacob in 1950. So that is what? Yes, that is the storativity or storage coefficient is equal to gamma W into B into bracket alpha plus n beta. So let us understand what are these terms. So yes, that is the storage coefficient, or it is a storativity. So it doesn't have any unit, so it is a unitless. Then what is gamma W? Gamma W stands for the unit weight of the water, that we all know, that is 9810 Newton per meter cube. That is the unit weight of the water, that is gamma W, into B. What is B? B is the saturated thickness of the aquifer, which is expressed in meters. So B stands for the saturated thickness of the aquifer. Then N stands for the porosity of the aquifer, that is again it is a fraction, percentage we express. So porosity is expressed in percentage, so it is a fraction. Then what is alpha and beta? So here beta stands for 1 upon kW. 1 upon kW is what? The reciprocal of the bulk modulus of elasticity of water. So that is kW, the value of kW is 2.1 into 10 raised to 9 Newton per meter square. So that is the value of kW, and beta is what? 1 upon kW, that is 1 upon 2.1 into 10 raised to 9 Newton per meter square. That is the value of beta. And what is alpha here? Alpha is also the reciprocal of bulk modulus of elasticity of what? The aquifer skeleton. Here beta stands for the bulk modulus of elasticity of water, and here alpha stands for the bulk modulus of elasticity of aquifer skeleton, that is the material which the aquifer is made of. So it varies with the material, that we have discussed. The different materials, different aquifer, different rocks act as an aquifer. So the material which comprises the aquifer, that depends upon the value of alpha depends upon the material of which the aquifer is made up of. That is so here alpha is 1 upon Es, that is reciprocal of the bulk modulus of elasticity of aquifer skeleton. So it varies with the material, it is not constant. Like we have kW value is constant, that is for water, that is 2.1 into 10 raised to 9 Newton per meter square. So here Es, it doesn't have any value because it varies with the material. So this is the formula for S, that is the storage coefficient. So you have to remember this formula to solve the problems based on it. So S is the storativity, that is storage coefficient, is equal to gamma w b into bracket alpha plus n beta. That is the formula for storativity. So here I told you the value of ES, that is the bulk modulus of elasticity of aquifer skeleton. It varies with material. So here in the table I have given few examples, few materials, and the bulk modulus of the compression of a few materials is given. Like for example, if the material, that is if the aquifer is plastic clay, then its bulk modulus of compression will be 5 to 40, that is 40. If it is a stiff clay, it will range from 40 to 80. If it is medium to hard clay, then it is 80 to 150. If it is loose sand, so see, you can observe one change that is happening here, that is as the particle size increases, the value of ES also goes on increasing. So here the unit for ES is Newton per meter square into 10 raised to 5. It is 10 raised to 5. So the loose sand, if it is, see, the sand is having bigger grain size than the clay. So if it is loose sand, it is the value of ES is 100 to 200 Newton per meter square into 10 raised to 5. If it is dense sand, it is 500 to 800. If it is dense sandy gravel is again bigger than sand, so it ranges from 1000 to 2000. And here if the rocks, if they are fissured or jointed, means if the rock contains cracks, okay, so it again increases, it is 1500 to even 30,000. Okay, and if it is a rock which is sound, okay, then it will be more than 30,000 also. So that is the bulk modulus of compression of few important materials of which the aquifer is made up of. Then the storativity or the storage coefficient is the fraction, okay, the fraction of storage attributable to expansibility of water. So here this fraction, it is attributable to expansibility of water. So water expands, okay, so wherever there is a condition of expansibility, you have to use this formula, that is SW, okay, that is equal to 4.7 into 10 raised to minus 6 NB. Or if the fact that yes, that is storativity normally varies directly with the aquifer thickness, and it enables the rule of thumb relationship. So there, if the value of yes, you can calculate as 3 into 10 raised to minus 6 B, where B stands for the B stands for the thickness of the aquifer, okay, B is the saturated thickness of the aquifer, okay, and N is the porosity. So here it is written B is equal to saturated aquifer thickness, that is expressed in meters. So these two formulas you have to remember along with the previous one, okay. So this formula is used when the fraction of the storage attributable to expansibility of water. So if the condition is given, that is expansibility of water, then you have to use this formula. And there is one more fact, that that is storativity, it varies directly with the aquifer thickness. So how much is the aquifer thickness? It varies with the thickness of the aquifer. So sometimes we have to use this formula also based on the conditions given in the problem. So now we'll discuss the two different cases: storage coefficient of confined aquifer and unconfined aquifer. So here in the diagram, first we will discuss the storage coefficient of confined aquifer. So here the diagram is given. You can see there is one cross sectional area is taken. Okay. Yes. So here the unit area, that is 1 square meter area, is taken. Okay, here this is the 1 meter by 1 meter cube is taken for observation. So this is confined aquifer we are talking about. So confined means what? When it is under pressure. So here you can see this represents the impermeable layer. Okay, so this is impermeable layer and this is one more impermeable layer. So this becomes the confined aquifer. So confined aquifer, that is permeable, so the thickness is B. Okay, and the aquifer prism yield, that is equal to S. So due to the unit decline of piezometric surface, the aquifer prism yield will be S. So here the piezometric surface is shown. Okay, piezometric surface, that is the original surface, and the piezometric surface falls by 1 meter. So we'll see this. Okay, because it is a confined aquifer. Okay, so this part becomes aquitard, that is impermeable material. Okay, so for a vertical column of unit area which is extending through a confined aquifer as shown in the figure, so the storage coefficient, that is S, is equal to the volume of water which is released from an aquifer when the piezometric surface declines a unit distance. So here what we are observing is the decline of the piezometric surface as shown in the figure, you can see. So here we have selected a vertical column of unit area which is extending through a confined aquifer. So this is extending through a confined aquifer. This here it is the confined aquifer. So this area is extending through a confined aquifer, so as shown in the figure. So the storage coefficient, that is the S, equals the volume of water which is released from the aquifer when the piezometric surface declines a unit distance, that is here. Okay, so here it is decreased by a unit distance. So piezometric surface falls by 1 meter, a unit distance. Okay, so it is a dimensionless quantity involving a volume of water per volume of aquifer, and the storage coefficient for a confined aquifer, it ranges from 0.00005 to 0.005. That is the range of the storage coefficient for a confined aquifer. So this happens in case of a confined aquifer. Okay, so here what we have observed is, we have taken a unit cross sectional area, right, 1 meter by 1 meter, that is extending through a confined aquifer. So here the aquifer is confined. So if this situation exists, then the storage coefficient will become what? It will be equal to the volume of the water which is released from the aquifer when the piezometric surface declines a unit distance. So that is in case of confined aquifer. Suppose if the aquifer is unconfined, what will happen? Again same. Here what we are, so for a confined aquifer, or it is also called as water table aquifer or water table condition, the storage coefficient is same as the specific yield as shown in the figure. So there if it is confined, it falls. Okay, here it is same as the unconfined aquifer. So here the value of the storage coefficient for a water table aquifer that is unconfined aquifer, it ranges from 0.05 to 0.30. Okay. So here we'll understand the diagram. Okay, what is given here? Storage coefficient or specific yield of a water table of a unconfined aquifer. So this is a unconfined aquifer wherein the impermeable layer is at the bottom, that is aquiclude, and on the top there is no such impermeable layer, so it is a unconfined aquifer. If it is at the top, like in previous diagram we have seen, okay, wherein there is again a impermeable layer at the top, that becomes the unconfined aquifer. Okay, but here it is unconfined aquifer. If it is sandwiched between two impermeable layers, that becomes the confined aquifer. Now here let us understand, we have again taken a unit cross section area here, that is 1 meter by 1 meter, 1 square meter area. Okay, so this is the normal groundwater table. Okay, and this is the water table which falls by 1 meter. Okay, water table falls by 1 meter when you extract the water. So that is aquifer prism, that is aquifer prism yield is same as the specific yield, that is SY. So for unconfined aquifer, or it is also called as water table aquifer, so here the storage coefficient becomes the same as what? Same as that of the specific yield of the aquifer. So the storage coefficient for water table aquifer, that ranges from 0.05 to 0.30. so these are the two situations. Okay, so the storage coefficient for a confined aquifer as well as the storage coefficient for a unconfined aquifer. So here in the next class we will solve some problems based on these all three definitions. Okay, porosity, permeability, storage coefficient, okay, specific yield and specific retention. Thank you.